Okay, if you're looking for this lesson in your note guide or what to title it, this is lesson 4.9 in your book. And it's about quadratic systems. So we're going back to what we discussed in our very first lesson. We talked about systems of 3 equations and 3 unknowns, and we've done that throughout this lesson. And then here what we're doing is combining that information and the knowledge we have about quadratics. So you'll see here that this system might look a little bit different than what you've seen before, because it not only has a linear piece, the y equals negative 3x plus 4, but a quadratic piece. But we still solve them the same. So we can use substitution or elimination. So in this case, with the way that the equation is set up, I'm going to go ahead and choose to use substitution. So I'm going to substitute the fact that y is equal to negative 3x plus 4 into the first equation. So I'm going to replace the y in the first equation with negative 3x plus 4. And on the other side, it already had x squared plus 3x plus 9. Okay. So here, I have a quadratic. Okay. And so my choices for solving quadratics are completing the square quadratic formula and factoring. I'm going to go ahead and set the equation equal to 0 by canceling the terms on this side and doing the same thing on the other side of the equation in order to see what the numbers look like and which method would be easiest for me to use. All right, so to solve this, I would want to go ahead and it looks like factor because this is factorable, and then that's pretty quick. Let me just check my factoring. If I do x plus 5 times x plus 1, that will give me that x squared plus 6x plus 5. And then if I set each of those equal to 0, I have that x could equal negative 5 or x could equal negative 1. Now remember what we're doing when we're solving systems. We are finding points where these things cross. So this is a parabola and a line. Think about these two shapes. And think about the number of times that they could cross. Okay? We basically could cross, if I move the line here, if it's where it is right now, you see they don't cross at all, and that's a possibility. It's possible that the line just hits the parabola at one spot. It's also possible that the line crosses twice at the parabola. So the fact that you have 2 x values, this is not one ordered pair. These are 2 separate x values, meaning this line and this parabola are crossing twice. At one of the points that they cross at, the x coordinate is negative 5. And at the other point they cross at, the x coordinate is negative 1. And now we need to find a y coordinate to go with both of those x coordinates. So I'm going to go ahead and take one of my equations. I'm going to take the linear one because it's a little bit simpler to plug into. And I'm going to plug in negative 5 for x and get 19. So that's one point of intersection. And I'm going to do the same thing plugging in negative 1 for x. And that's going to give me 7. So these are the 2 points of intersection for this system. All right, so let's look at part B. We could take the same approach here. Okay, so I see the same type of system, which again means there could be 2 places of intersection, 1 or none. And I'm going to go ahead and do that same type of substitution in this system. And again, to solve the quadratic, I'm going to set it equal to 0 to see which method is going to help me the best. So I tried factoring, but then if I use 2 negatives to multiply to make this positive 4, they don't actually make negative 3 in the middle. So I decided I would use quadratic formula because it doesn't seem factorable. So negative b plus or minus square root. So b squared minus 4 times a times c all over 2a. As I simplify this, In my radical, I have 9 minus 16, which is negative 7. So right here, I would have two x values, but these two x values would be complex, meaning right here, because the negative is under the radical, they would have an imaginary part, which means if there aren't any real solutions, these are not places that they cross on the graph physically. So in this case, since I'm looking to solve the system and find those real numbered coordinates, they don't exist. So in this system, there would be no solution. All right, looking at the third example, we have two quadratics, but again, I could take the same approach as before. I can set negative x squared plus 3x plus 7 equal to x squared plus 9x plus 7. And when I do this, I'll go ahead again and move everything to the same side to see what I am really dealing with. I'm going to have 0 equals 2x squared plus 6x. I'm going to go ahead and solve this one by factoring again because it factors to 2x times x plus 3. And if I set each of those factors equal to 0, I get that x could equal 0 or x could equal negative 3. So think about what's happening here. These two original shapes were parabolic. So you have two parabolas, one concave up and one concave down. It's completely possible for them to cross twice. And so you're finding x coordinates here of the 2 points they cross at. So again, that means we have 2 points of intersection. And we want to find those y coordinates. So we'll take one of the equations. I'll take the first one, and I'll plug in 0. And I'll get 7, so the point 0, 7. And you can check that that point exists in the second. Well, it should, because remember, your solutions to your system should work with both equations. And if we plug negative 3 into that equation, we have to do a little more work to get our answer, but we have 9 minus 27 plus 7. So this is going to be negative 18 plus 7, and that's going to be negative 11. So these would be our 2 points of intersection here. Now, in the directions here, it said to confirm your solutions using your graphing calculator. So what we're going to do is take a look at another function that the graphing calculator can serve. So if we turn on our graphing calculators, and we go to y equals, and let's say we put in both of these equations from example 1c. So if you're like me and you had this on shading, you're going to want to go ahead, press enter over there until the cursor gets back to just being a regular line. Okay. And then we want to go ahead and type in our equation. So our first equation was x squared plus 9x plus 7. And our second equation was negative x squared plus 3x plus 7. Now I'm going to go to Zoom and choose choice 6, the standard window, and see what I can see. Now remember, my purpose here is to see points of intersection. So I can see them, but not that well. I want to see this lower one a little bit better. So I'm going to go to Window, and I'm going to have my y minimum go down further than negative 10, maybe like negative 15. And now I see the 2 points of intersection. Okay. So to calculate those, we're going to go to Second, Trace, or Calculate, and we're going to choose Intersect, choice 5. What it's going to do is it puts you on a curve already. Okay, so you can see if I move left and right, I'm on one of these parabolas. Okay, you can see my cursor traveling along. What you do is put that cursor as close as possible to the intersection point and press enter. After you've pressed enter, it switches you to the other curve. So now if I move left and right, you can see that I'm along that other curve. Again, I want to get close to the intersection and press enter, and then press enter for it to guess. And so it says negative 7.03 e to the negative 14. So that's like scientific notation, like 10 to the negative 14th power. So that's like 0.00000, 13 zeros, and then a 7. So that's basically like 0.7, which is what we got. And then we would repeat this for the second point of intersection. So I would travel down to that curve and press enter. It switches me. I would get as close to the intersection as I can again and press enter for it to guess. And then you'll see we have negative 3, negative 11. So that should confirm on your calculator what's going on. Okay. And then on your note guide, the last thing I want to do is look at if they are inequalities. And for this, basically, you're graphing both inequalities together like you would if you were just graphing one. There's just two of them. So for my first equation, the y is greater than or equal to x squared plus 5x minus 8. Okay. You would find vertex, and when you use negative b over 2a, you should get negative 5 over 2, and when you plug that back in, you should get negative 57 over 4. Okay. So our vertex is going to be at negative 2.5, so like here, and then negative 57 over 4. So 57 over 4 is like, let's see, 14 and a little extra. So it's going to go below my graph, way down here somewhere. So 2.5, negative 14 something. And then plug in to get another point. So I'm going to use the y-intercept. So if I plug in 0, I would get negative 8. And I'm going to mirror that on the other side. And this would be my parabola with a solid boundary. Solid because the inequality says it could be equal to. And then if I plug in 0, 0 as a test point, it works. So I know that this inequality would be shaded here. So then I'm going to graph the second one. I'm going to go through the process. So the vertex here ends up being 3 over 2, 25 over 4. Okay. So that's positive 1.5 and then 6.25. So 1.5, 1, 2, 3, 4, 5, 6.25. It's up here. So there's my vertex. And again, I'm going to find the y-intercept as the other points, and the y-intercept here is going to be 4. And mirror that on the other side. And my boundary will be dashed instead of solid because the equation does not say it could be equal to. Again, I could test 0, 0 as a point, and it works again. So the shading for this equation is down here. Okay. So the solution set that we're really looking at is right where the shading overlaps, okay, which is all of this part right here. So any point within those boundaries is a solution. If it's on the solid boundary, it will count because that's included. If it's on the dashed boundary, it would not count as a solution. So to list a solution in the set, I could say like 0, 0 is a solution. You could list any other point that's in that shaded region.